electronics, things get complicated. We could end up building a circuit like this. I just put something randomly together, and then we need to plug it into our system. Usually we refer to this as the load. But before we plug it in, we need to make sure that what we're putting across the load is okay, reasonable, and safe. And this is where Thevenin's theorem comes in, where we try to extract what the voltage across that load would be and the resistance that it experiences. We want to get a certain perspective out of our circuit, and we can do that all thanks to a gentleman named Leon Charles Thevenin. Although technically it was actually Helmholtz who developed the original Thevenin's theorem derivation, but Helmholtz was a physicist, and so it was a very physics description, and not many people were able to apply a lot of the knowledge. Thevenin separately developed Thevenin's theorem, where he was the director of Telegraph Engineering School, and supposedly a very good violinist. He passed away in 1926, and it was only right before his deathbed that he realized that people were using his theorem. He had developed it, didn't really think about it at the time, and a friend was visiting him while he was retired and told him that everyone was using his application in circuits. If you know anything about physics, you would know that a lot of people's ideas, theories, and experiments weren't accepted until way past their passing, so at least this has a little bit of a happy ending. Today I will show you how to apply Thevenin's theorem to a classical DC circuit and a classical AC circuit. These examples are a little bit simplified, but the premise can be applied even for complex systems. So let's get cracking. Let's always start with the easy one, DC circuits. Here I have a DC circuit diagram. We have a voltage source, resistor 1, resistor 2, resistor 3, and resistor 4. The load, or the thing that we want to analyze what it is experiencing, will be just RL, a resistor. Most things are just resistors anyway. So our goal is to measure what the voltage is across this area and what the resistance is in this direction. First of all, we're just going to remove the load and measure the voltage across these 2 points. Looking at that diagram, we're basically just measuring the voltage across R2 and R3. You might be saying, wait a second, Tofu, what about R4? The way I like to teach things is applied and practically. Literally grab a voltmeter and measure this circuit, but also think about what a voltmeter is. It's basically just a giant ass resistor. If you put it across, just have a 580 ohm resistor in series with another giant resistor, let's say infinite size. Infinity plus another number is just infinity. So there is no current being passed through here. Hence, we're only measuring the voltage across these 2 resistors, R2 and R3. So to measure the voltage, it's the classical voltage divider equation. We want to measure what the voltage is across R2 and R3 over the total sum of all the voltage drops, R1, R2, and R3. They should all add up to 10 volts. Sub in the value of all of our resistors and the voltage source, and we get our voltage to be 5.41 volts. We're halfway done. The next step is to measure the resistance that this body will experience. So let's look at our diagram again. You're not measuring the resistance of the total circuit, but rather, what is the resistance from the perspective of the load? You start here and follow the path of the current. The first resistor you meet is R4. Ta-da! The next resistor you meet is 2 resistors in parallel, R1, and R2 and R3 in series. If you want to make this a little bit simpler for yourself, you can do an equivalent resistance of R2 and R3. Because they're in series, you can just simply add them up. What I've done is I've kept track of it the whole way through. Sub in your numbers, and the answer that you get is 970 ohms as the Thevenin resistance. DC does tend to be nice. Here we go with AC. Don't get too scared. Some coffee. For the sake of fitting everything on one whiteboard, I've decided to have only 1 resistor and 1 inductor. I am working with the premise that you have done introductory to AC circuits and introduction to inductors. You do need to have completed waveforms, phasor diagrams, inductors and capacitors as lagging and leading circuits. The premise remains the same. We want to know what Thevenin's theorem is, i.e. its voltage and resistance, across what this load would experience. We want to get the point of view of this load. Do the same principle again. It's a voltage divider equation. Ultimately, what we're doing is we're measuring the voltage across the inductor, impedance of the inductor, over the total sum of the impedances. The resistance of a resistor is resistance, the resistive of an inductor is reactance, and complication summation of them is impedance. For the sake of this video, I'm going to refer to everything as impedance to just keep it consistent and make sure I don't make a mistake. The problem here is that we have polar form and rectangular form. And if we want to do multiplication and division, we need it all in angular form. Now, there are formulas in your textbooks that help you with this. And personally, I despise them because I dissociate and I have no idea what's going on most of the time. So for me, I logically draw it out. I know what a phasor diagram is. I know that an inductor is positive 90 degrees off a resistor and a capacitor is minus 90 degrees off a resistor. So what I end up doing is capitalizing on basic Pythagoras' theorem. I draw out the vector for the resistor and I draw out the vector for the inductor, 100 ohms and 40 ohms. Ultimately, we're looking for this angle here and the magnitude of this vector here to get it in polar form. Classical c squared is equal to a squared plus b squared, and we get 107.7 ohms. The angle is just classical trig, opposite over adjacent, that's tan. Arctan 40 over 100, our angle is 21.8 degrees. We can now sub it in for the rectangular form earlier, and we can finally do a bit of mathematics. 40 divided by 107.7. Angles we do not add or divide, we subtract. So that would be 90 minus 21.8, which gives us an angle of 68.2 and a voltage of 9.3 volts. Halfway done. We're going to continue with the exact same principle as earlier, but this time we're going to measure the resistance across this load in an AC circuit. So let's look at this circuit. Start here. Oh, our path splits. So basically we have a resistor and an inductor in parallel. Your formula for resistors in parallel, R1 multiplied by R2 over R1 plus R2. Ta-da! It's the exact same thing, but in polar and rectangular form. You have to do that because it is an AC circuit. It's a bit more complex. We have the exact same problem as last time. We have a rectangular form and we can't do addition and multiplication here. This is such a simple circuit that we don't actually have to repeat our steps here. It's the exact thing I did earlier. Subbing in the values, we can multiply and divide the magnitudes as always, but make sure to subtract and add the angles accordingly. If the values are being multiplied, we add the angles. If the values are being divided, we subtract the angles. Our final answer is 37.14 ohms, forgot my unit, at an angle of 38.2 degrees. Circuits will get more complicated, and chances are if you're a student and studying for exam, it will be a little bit harder. But the premise remains the same. If you have knowledge of phasor diagrams, potential dividers, your resistance formula, you can solve majority of circuits. Happy circuiting!